I welcome everyone to the 2025 IEEE Online Forum on Climate Change Technologies, and thank everyone for participating. So we encourage the participants to place the questions in the chat box during the talk. The second session of today's talk is by Professor Shankar, and he's a research technology manager at the Stanford Linear Accelerator Center as National Laboratory, and he has very extensive experience in materials research and microelectronics. And also he's an adjunct faculty at the Stanford Material Science Engineering Department. And with this small brief introduction, I invite Professor Shankar to briefly introduce himself and deliver the presentation. Professor Shankar.
Thank you, Dayalan and Mitradeep, for inviting me to the talk. Looking forward to sharing some different ideas about computing and energy. I may answer some of the questions that was asked of the previous speaker, Simon, as well. It may answer some of the questions. Can you hear me?
Yes, I can. Please.
Okay. So this is partially funded by the US Department of Energy and SLAC National Lab, and we also have funding from other supports as well. There are a few collaborators who have contributed to the work, and there is a lot more work that I am not speaking of, but I can get into if there is interest. So the outline of the talk is divided into 4 parts. I will talk about the primary trends, which essentially says why the current growth in computing is not sustainable. And then I will also talk to a couple of other trends which are hidden, which essentially also makes computing unsustainable on the current trajectory. And then on paths forward, we will talk about why computing itself may need some sort of reframing. And then I will summarize. So let's talk about the trends. So there are about 8 trends I have looked at over the past few years on computing. First, on climate change driven constraints on computing. This is real, and then the second one is on applications driving the computing needs, that scientific, cryptocoin mining, and AI. Then energy conversion inefficiency, that is from no matter whether you take sustainable sources or fossil fuels, you still have a conversion inefficiency when you convert it into electricity. Then the economics of compute, data requirements in AI training, compute inefficiency, algorithmic scaling, and semiconductor technology constraints that are happening, of which I will talk about these because given the finite time, and the rest of it, if there are questions, I can talk to that. So we'll start with the applications part, the hardware, accelerator, and supercomputing analysis. So the extreme computing, where computing is currently reached, is anything at the exascale and above. Exascale is 10 to the power 18 operations per second. And we will kind of touch upon that now. So this is actually the energy of the 2 biggest supercomputers in the world. Frontier in Oak Ridge, which operates at 1.1 exaflops, consumes 21 megawatts of power. And Aurora in Argonne National Labs has 2 exaflops and runs with 60 megawatts of power. What is interesting is the advanced photon source in Argonne, which is essentially what is used to be analyzed by a computer. The photon source is only 20 megawatt power. The computer that is being used to do the analysis is 60 megawatts of power. So you can actually essentially see the disparity in the power requirement. This is essentially the annual electricity used by select countries throughout the world, of course. And this is the total yearly usage. I have tried to mark certain countries. The unit is in terawatt hours. So this is just the electricity usage. And by the way, the electricity usage of a country correlates with the GDP. So higher the electricity usage, the GDP ends up being higher, shows the industrialization at some aspect. Now, if you take the two computers that I showed and make the top 500 supercomputers, which are considered the top 500, if they all become exaflop machines, the annual electricity consumed is given in the turquoise colored histogram. So you can essentially see that it consumes more electricity than several countries. If the 500 supercomputers were to be all at 1 exaflop, if all the 500 supercomputers were to be at 2 exaflops, which is what everybody is going towards, the total electricity consumed by just the 500 supercomputers is more than the continent of Australia. So the electricity usage is so high that only 2 countries in the world can host just the 500 supercomputers. Now, this is the same thing, what I said. This is comparable to electricity consumed by entire countries, actually, and even continents, as you can see. And about 67% of the electricity consumed by the UK is just consumed by these 500 supercomputers. Now, if you go to the next supercomputer, zeta scale, that would need 21 gigawatts. So that would be approximately 21 nuclear power plants. And this essentially is the total electricity that would be needed. And this is about the typical time duration between 2 generations of supercomputers are like about 14 to 15 years. So the zeta scale computer is more around the 2030s time, and you can see that it will essentially consume more, the equivalent of 21 nuclear power plants just to run a computer. Okay, one computer, not 500. Now let's kind of go back and see what has actually happened historically. This is taken from 1970. I think all of you know here about this is Moore's law. The blue is essentially the number of transistors. The y-axis is logarithmic. The red is the frequency. So if you look into it, you will essentially find out that frequency has been flatter since 2000s, while the number of transistors has gone up. And that is how the performance per watt essentially has been doubling with a constant power, nearly constant power, not constant power. If you double the number of transistors, you can essentially get more performance per watt. And this is what the Moore's law has essentially enabled this. Now I'm going to show you in the last 10 years, the energy for a single transistor level switching. So the x-axis is going from 2010 to about 2022. The y-axis is the energy per operation in joule. In the case of transistor, it's energy per transistor per switching. Okay. The thermodynamic limit is approximately at 4.4 times 10 to the power minus 21 joules. And if you look at the most recent transistor, it is closer to 10 to the power 18 joules. So it is close to attojoules now, which means it's about 2 to 3 orders of magnitude higher than the thermodynamic limit. Now, if you look at the energy for chip level switching, so what you see here is essentially different precisions in the instructions. The red circles are floating point 64-bit. The blue are 32-bit. And the crosses are essentially integer, 4-bit, 8-bit, and so on. So you have going from 4-bit to 64-bit through the same decade that I'm showing the transistor. So as the transistor is essentially dropping energy due to Moore's law, you can essentially see that the floating point operations are still approximately about 6 orders of magnitude higher per instruction. Okay, this is per instruction. You will also see that lower precision is much more energy efficient than higher precision. And if you multiply a 4-bit by 16 times, you still don't get the energy of the 64-bit. It's much more expensive to switch a 64-bit instruction. Now, if you look at the energy of supercomputers, the top 500 that I showed you, the benchmark that is used for supercomputer is something called Rmax and HPCG. If you look at that, you find out that the energy of the supercomputer is even high, as you can see. So over the same 10 years, as you go up in systems, the energy keeps increasing. Now, I'm going to show you on the algorithm side as well, which is essentially taking analysis from ChatGPT. So this is taken from a presentation from Japan. It essentially says that the cost of GPT, that is an AI-based, large language model-based AI formalism versus scientific prediction. So the GPT-4 is estimated to take a whole year to have a 32-bit prediction of weather. That shows that AI is not necessarily the most efficient way to do scientific computations. This is the analysis made at Tokyo Institute of Technology. So this is actually showing on the x-axis the number of parameters needed, and the y-axis is the accuracy. You can see that the parameters have exceeded 1 trillion now, but I am showing up to 175 billion. And you can see that the curves are not asymptotically going, which means the accuracy can continue to increase as you increase the degrees of freedom or the number of parameters. So now I'm going to show you an estimate of the energy it takes for training and the energy it takes for inference. The energy per floating point operation, if you assume based on the analysis I have shown you, you can take the minimum of that and the maximum of that. You can assume that about this analysis is actually outdated already. This is an analysis from 2023. And you use the number of words per day and number of bits per day and number of floating point. I have shown you the assumptions we used in the calculation. And rough estimate is about 4.5 billion words per day are generated by ChatGPT. This is the energy in kilowatt hour. The y-axis is again logarithmic. You will see two histograms for each one. That is the lower limit and the upper limit. The training takes up to 1 million kilowatt hour. It takes about 55 days to do a single training based on 2023. This is ChatGPT 3.5. The inference, although the inference lower limit is lower than the training, you can see that the inference higher limit is closer to that of training because inference is running around the clock through the whole year, while training is done for focused about 55 to 60 days at a stretch. Compare that to electricity consumed per household, and the red is essentially an entire human's energy spent through his or her entire life is still 3 orders of magnitude, about 2 to 3 orders of magnitude lower than that of a ChatGPT inference alone. So it tells you, just to give you an idea. Now, the same plot which I showed you in terms of the hardware, I have plotted it here. The y-axis is energy in joules. The purple colored histogram is the thermodynamic limit at 300 Kelvin. The green is the biological unit of information processing. That's a minimum biological unit. ATP to ADP conversion, that's approximately of the order of 10 to the power 19. it is between 10 to the power minus 20 and 10 to the power 19. And as you go into transistors, you have two blue colored histograms. Then you go to instructions, you can see that the energy increasing. Then as you come into the orange colors, you see its floating point. And then you come into supercomputers where the benchmarks, higher end benchmark, you can see that the energy per instructions continue to increase. Now I add software and the algorithms to it, and now the energy essentially has gone another 12 orders of magnitude. So you can see that the software is on the right-hand extreme. I have three examples. One is a scientific computation of a COVID-19 virion protein that got a Gordon Bell Prize. Then a single crypto coin mining electricity, and then the NLP training that I showed you. Okay. So this is 27 to 36 orders of magnitude as you go from a single transistor to an entire simulation. Now this is per simulation, okay? The y-axis denominator changes as you go down. For transistor, it's a single bit. For the instructions, it's per instruction. For the simulations, it is per simulation. And this is important because it gives you metrics to measure for energy. So now there's an inefficiency in data centers that I will talk about. This is actually the efficiency in energy conversion between different sources of energy. So the y-axis shows you the conversion from electricity to thermal at the top, and at the bottom, thermal to electrical at the bottom. So electrical energy has the highest quality of energy, while the thermal has the lowest quality of energy. So computing converts the highest form of energy or the highest quality of energy to the lowest quality of energy at the speed of compute. Okay. So that is an important factor because that kind of tells you to the data conversion in data centers, which I will show you. This is an example of a data center. So in a data center, computing has a multiplicative effect. We hypothesize that there is a 3E effect. That is, every unit of compute needs 3 units of energy. First to compute, second to cool the heat generated, and the third is the building block for the entire electronics that goes on the data centers. That was our hypothesis. And the data center electricity needed is expected to double by 2030, as you can actually see. Okay. Now, so this is actually taken from a cooling circuit. I mean, I took the picture from a cooling circuit. The cooling circuits in data centers have become as complicated as the computer wiring circuit itself, because cooling is an important thing. And what you are seeing is an accelerator, not even the mainframe computer yet. It's just an AI accelerator. So here is the electricity conversion efficiency from different sources of energy to electricity. You will see that our hypothesis was it should be a 3E effect, that every unit of compute needs 3 units of energy. But in reality, it ends up between 4 and 5. In other words, every unit of compute, no matter what your source of energy for the data center is, it's only like 25%, 20 to 25% efficient when it actually converted into electricity for computing. And as I also made a point of saying that the electricity itself, as you go higher in systems, the efficiency goes down. And I'm going to show you that a little later. Now, there's also another thing on data requirements. So I'm going through different trends. Okay, I told you 8 trends, and I am going through about 5 of them in the presentation. So these are the data used in GPT. 3 training, you can see that most of the training is essentially coming for 175 billion parameters need 300 billion training points. Okay. And the floating point operations needed are 3 times 10 to the power 23. Okay. That is how much is needed for training. And the reason is because the distributions that essentially ChatGPT and other AI platforms are trained on is called power law, not a normal distribution. If it were a normal distribution, you can essentially do it with 30 points. But given the Pareto nature of the distribution, you essentially need huge amount of data for all of them. And this is an example of English language. The y-axis is the frequency of the words used in the language. The x-axis is the number of words. English language has about 175,000 words and colloquially about 300,000. But as you can see, the tail of the distribution keeps growing because more and more words get introduced in the language and in the lexicon. So you cannot just fit it once and use it. You have to continuously train it because the usage of that could change with time. And this is to show you the actual example. Y-axis is the floating point operations. The x-axis is the year. The number of floating point operations per parameter has been increasing as well. So you essentially have gigantic amount of number of operations needed, and the total flops are given in blue circles. And you can see that's of the order of 10 to the power 24. Now, if you go to chemistry, so I showed you this for English language. That is where the large language models are trained. Now, if you go to something like fluid flow for weather prediction, they also follow a power law. What is shown as the Kolmogorov scale, and the x-axis is the frequency and the y-axis is power density. You can see that that also seems to follow a power law. If you go into chemistry and materials, the number of chemicals or materials are of the order of 10 to the power 30. So they also follow a power law. So in other words, no amount of AI training can essentially compactify this problem because of the very nature of how some of these combinatorial problems are laid out in science. I mean, there's a little bit more to it, which I will talk to shortly. Now, let's look at the semiconductor technology. So people say that Moore's law can essentially scale and make it more energy efficient. And let's go a little bit deeper into it. What is shown here is 6 different precisions. Integer 4, integer 8, FP16, B float 16, FP32, and FP64. 12 different companies' products are looked at in terms of joules per instruction. The x-axis is the year. So this is mostly in the 2010s. So you can see different products, and we will kind of focus on some of them. You will see that the floating point instructions are more energy intensive, consistent with the previous analysis that I showed, except for FP32 and 64 across year versus same year are of the same order of magnitude, which means there is no efficiency increase in precision. And within a given technology, oh, I forgot to tell you one more item. The bigger circles means older technology, smaller circles means newer technology. And I will kind of show that to you in the next slide. So the smallest circle is 10 nanometers. The bigger circle is 25 nanometer. Now, if you look at that blue ellipse, you will see that the smaller circle is higher energy than the bigger circle, showing that older technology can have lower energy per instruction. If you look at the purple colored ellipse, it essentially shows that there is no difference. And if you look at the green ellipse under FP32, you will see that in the same year, older technology on a different architecture can be more efficient. In other words, you can use architecture to be more efficient, even if the technology is old. And that's what we are seeing. And this is same as what David Patterson and John Hennessy have it in their paper as well. We are just empirically observing that to be consistent. Now, why is computing this energy intensive? So let's dig a little deep into it. And I'm going to show you two things. These are what I called hidden trends, and we will look at both of them. So bits and instructions, the number of bits switching per second relate to frequency of the transistor. At the system level, the corresponding variable is the number of instructions. So we actually look at the instructions per second and bits per second, and it kind of gives us a clue as to what is actually happening. So this, on the y-axis, you essentially have bits per instruction. How many bits do you need for a single instruction? In other words, how many transistors are you using to execute a single instruction? And the number varies from 10,000 to 100 million. And what is worse is you see it actually increasing. In other words, you are using more and more bits per instruction in order to accommodate the complexity in the architecture and the algorithmic needs. If you had an ideal system in which you used 3 bits per instruction, that is fetch, execute, and store, then you will have a curve that is on the horizontal axis, which is given as this maroon colored circles. But as you can see, we are overutilizing the bits in terms of that. And this gives one of the clues of that. This is the same thing, but it also has a finer resolution to show that the 4-bit integer is much more energy efficient than a 64-bit floating point. It is more than 16 times efficient compared to a floating point 64. In other words, a lot more efforts are being spent in making lower precision instructions more energy efficient. That is the conclusion of that. This is the same thing, but shown through the years as to how things are changing. Now, I mentioned that as you go up in systems, your energy continues to increase. So this plot on the y-axis is energy joules. The transistor, blue is the lower limit, red is the upper limit. As you go to a DRAM storage, floating point operations, on-chip communication, off-chip communication, reading DRAM, and then internet routing, internet access, wireless, wired, and you can see that the energy has increased by 15 orders of magnitude as you go up into communication. So from transistors to system, all of this adds up to get the same bit to communicate. You're spending a lot more energy. Now let's look at algorithmic complexity. So x-axis is the number of entities and y-axis is the number of computations you need. So petascale would be a line, horizontal line through 10 to the power 15. Exascale is 18, yotta-scale is 24, and quettascale is 10 to the power 32. Typically, it takes like 14 to 16 years between the two scales for computing, okay? So these are all the entities that you want to simulate. So these are highest end supercomputers, let us say. the number of units you need to compute different scientific problems, going from action potential in a neuron to number of cells in a human brain to number of reactions in a human to number of molecules in a mole for a chemistry problem, total number of reactions happening in a human to a number of organic molecules. They are vertical lines because they are the number of units. So now let us look at linear scaling of algorithms. If you have all algorithms linear scaling, these are the only problems you can solve even at iota scale. Okay. If you have polynomial scaling algorithms, the number of problems you can solve get fewer because of the nature of that. And if you get to NP hard problems, this is all you can solve. In other words, the current trajectory of computing, even if it went to iota scale, the number of problems you can solve become limited because the algorithms scale a lot more severely than either the Moore's law scaling or your energy efficiency scaling. Okay. So then why does computing needs reframing? I showed you this, but I'm saying it in a little different way. It's the same number. The energy scale going from a transistor to application goes from 27 to 32 orders of magnitude or even higher. So part of it is, in order to understand this, we need to go back to thermodynamics and chemistry and physics. Heat engines, since 1824, Carnot's engine is essentially what the Industrial Revolution was facilitated by. The heat energy is converted to heat and mechanical work. That's what ACs, refrigerators work under these principles. All of nature converts chemical energy to mechanical energy, heat energy, chemical energy, and information processing. This is what nature does. Computing, if you were to look at it like another engine, it converts electromagnetic energy to heat energy and information processing. Okay. Now, the y-axis here is given energy in joules. So now we are going to the physics and chemistry. The first ones are the energy of a chemical reaction. The second one is a quantum estimate of a chemical configuration, the energy required in joules. This is the energy of a single transistor. That's about 10 orders, not 10 orders, 10 times more, an order of magnitude higher than a quantum energy. If you look at a synapses in a human brain, that's approximately the same order of magnitude as a single bit switching these days. If you use a quantum computer to do that, we can estimate the energy to be this. If you use a classical computer to simulate the same chemical reaction, you see essentially this energy. In other words, which application you want to simulate determines what computing framing you need to use for that. So a quantum computer is more appropriate in terms of energy efficiency for a quantum simulation, but may not be necessarily efficient for weather prediction. And that is why the reframing of the computer comes into it. So based on this, our lab has essentially classified the entire computing into 4 domains: the microelectronic systems, quantum information based in blue, nature inspired in green, and algorithms and software gets its own dimension or a domain. If you essentially make the estimates of energy, the center is the thermodynamic limit. That's a minimum energy. You cannot go below that. You can essentially get a 100 million X efficiency from the architecture and the hardware alone. And that is what that number is. So you are 100 million X more, and you can essentially bring it down. If you look into quantum information based, you can get 10,000 to 10 million x lower. If you look into nature inspired systems, you can get 1 to 100 million. And if you look into the algorithms, that is where the biggest bang for the buck seems to be. Algorithms are the most inefficient and they can essentially be brought down. So, summarizing this, energy and resource requirements are on a trajectory that appear unsustainable. Increasing miniaturization and economics of scaling needs to commensurate with user needs, and data requirements seem to be very high. The factors leading to these trends are multifold. Everywhere, digitalization is spreading across all layers of economy, and the geometric-based scaling known as Moore's law or Dennard's law is slowing down. So the root causes need to be addressed. So computing may need reframing consistent with other domains of information processing, as I tried to show. So design for low energy and energy efficiency should be part of it. I did not go into semiconductor manufacturing, but there's a whole bunch of analysis that we have done. Most of the microelectronics processing energy, 80% of the energy, 80% or higher can be attributed to the EUV. And the remaining 20% is to the processing. And there you can be a lot more efficient in processing. So with that, I can actually stop and address any questions.
Thank you, Professor Shankar, for the interesting talk. So we have time for questions and some discussions here. So I think the first interesting comment and question made by Professor Ravinder, and if you can see the chat box, I can read it for you. So he says, I'm wondering if we need to revisit computing architecture to reduce the hardware and hence the energy. For example, using lesser number of transistors, he says examples is weightless neural networks for the same function. The use of traditional digital architecture for generative AI requires considerable energy, and the pace of growth raises questions about sustainability. Your thoughts, please.
Yes, so we are actually testing in my lab. I am also setting up a measurement lab to be able to measure this. One of the things we are actually testing is spike neural network based ASIC. And we are finding out that it is very efficient for spike neural network based problems. So the application and the architecture, for want of a better word, I would call it resonance. If the architecture resonates with the application that you are simulating, then it seems to be highly energy efficient. So I agree with that statement wholeheartedly. And we are actually observing it. But that shouldn't be surprising because nature does that all the time. Nature is able to process information in the most efficient way. And that another example is analog versus digital, that it's an age-old battle. Signal to noise ratio in analog is considered small, but nature uses analog using hierarchically encoded information. It's not just analog computing, it's digital within analog. So it does very intelligent ways of information processing. And that is what I mean. There are a lot of lessons that you can learn from nature and implement it at the architecture level, and also implement it at the algorithmic level, for example. Using a general purpose large language model for every problem seems like an overkill. And this is what I tried to show you. The power law means that language is a problem. But that power law is not the power law of weather prediction. That's a different power law. That's a Kolmogorov power law. This is called Zipf's power law. They have different tails. So if I am going to be training something for one and expect it to be used for the other, I will be humongously inefficient. And that is what we are trying to say here.
Thank you. So we have a scope for developing nature-inspired architectures in the future for solving this problem. Okay, so this is out of the four strategies you mentioned. I think one of the strong strategies. I think the next question is from Professor Simon. I think he says a main concern is somewhat political, and why do we need such huge data centers to solve this problem?
Yeah, you know, especially those of us in the US, we just cannot answer that question in a public meeting. But I think Professor Simon probably knows this as well as anybody else does. I mean, we have over $500 billion are going to be spent in the US on data centers. My worry is not the use of data centers, but I just tried to show you that computing is intrinsically inefficient in terms of bit utilization and energy usage. So bit switching is energy efficient. Bit utilization is inefficient. So building data centers use the current paradigms of modeling, current paradigms of computing may not be, we may end up revisiting this is how I would put it.
And the previous, following the question from question from the session of Professor Simon, moving towards post-silicon materials, like using 2D materials to build computer architectures. And what's your thought on that? Does that have a scope?
So here's, this is a question you can answer based on what I'm going to tell you now yourself. So if the 2D material is used as an interconnect versus 2D material used as a transistor, let's take the transistor first. Transistor is already operating very close to its limit of computing, 10 to the power minus 18 joules per transistor per switching using silicon 3D high K. It's happening today. M4 processor is incredibly efficient energy-wise. So if I did 2D, let us say, it will increase it, but there's not that much more margin for me. There's about 10x there I can go down, right? But if I go to the interconnect, my energy is 10 to the power minus 15 to 10 to the power minus 12. So 3 to 6 orders of magnitude higher than what the energy is, not because the interconnects are inefficient. I am fetching huge amounts of data from memory to compute. So taking the compute to memory will give you a bigger bang for the buck than 2D material, is my thinking. That doesn't mean, so it is like you are using millions of pennies. That's what the transistors are. Each penny, if it becomes more efficiently processed, then they add up to energy efficiency overall. So having a transistor more and more efficient, we should never give up because that adds up. Because I showed you that we are using 10 million bits for a single instruction. So if each bit is more efficiently processed, it will add up. Pennies will add up to become dollars, and dollars will add up to become thousands of dollars and millions and so on. So there is an efficiency to it. So that's the way I would put it. It's not misplaced or anything. It is a great idea. But on the other hand, the bigger bang for the buck seems elsewhere, is my argument.
Yeah, even though I think the 2D materials are not really matured enough to produce at a larger scale to develop such architectures. So
Right.
that's also a bottleneck there at the material side.
Right. Even if I think it is needed mainly because what is after the high K or what is after the gate all around? You may need some kind of new things, but 2D materials have other lot of integration challenges because they are by van der Waals forces.
Right.
And they are non-localized electronic conduction. So if you have functionality destroyed anywhere on the 2D, the overall transport could get affected. Those things. But scientists and engineers in this microelectronics industry are incredibly clever. they fix
Right.
the problem. So I think it'll get fixed.
And to your view, the quantum computation architectures will never meet for conventional applications. You said for classical
Right,
applications,
right. So
it will
so
be.
so I will give you an example, and you will see why I am saying what I'm saying. Let us say you want to use quantum computers to search internet. You will hear a lot of people talking about it.
Mm.
All your data is in the classical domain. In order to search it, you need to upload it into a quantum system where all the search data needs to be entangled. That's a gigantic ask. Zettabytes of data needs to be encoded into quantum system operating at millikelvin to do just a search. Are you going to get your bang for the buck? But on the other hand, as I tried to show you, if you use a quantum computer to simulate a quantum chemistry problem, I mean, I was directing materials design at Intel. The biggest problem we had in materials was predicting correlated states.
Okay.
Exchange correlations are a very hard problem. Exchange can be fixed reasonably, but correlation is very hard. Quantum computers can solve correlation very self-consistently. So that alone, it will be useful. So you just need to be clever about which computer to use what. You don't take there is no Swiss Army computer, Swiss Army knife computer. Each one you need to get its own Phillips screwdriver or a hammer or a nail. That's what computing is starting to be. Patterson and Hennessy, in their paper, they call it the Cambrian Revolution in computing.
Right.
But they are saying it will happen all in architecture. I am saying it's not just going to be architecture, it's going to be even the form of computing. It's going to be in the algorithm, how you encode the algorithm and how you get the architecture. Architecture they have spoken to, but I am saying there's also informational basis, algorithms and software and bit switching. All of that needs to be tailored to an application.
Will there be again integrating a quantum computation architecture and a classical in the same
So we are
platform?
looking into it in my lab. We are trying to measure this. I don't know the answer to it. I think I expect a lot of issues and problems, but I would like to measure it and then get back. So if I have the numbers, I can more confidently tell you what the problem is. We are in the process of setting up a measurement in our lab for exactly
Oh,
that quantum
okay,
classical interface.
that's good to know. Okay. And one more point you raised in your talk, the heat circuits are very complicated for the supercomputers
Right?
thing. So the thought occurred is that since there's so much of heat generated at this closed space, will there be a possibility to construct a kind of a thermoelectric module with the systems? So the highest form of energy, electricity, is transferred into a poorest form of the heat energy, which again convert you can convert that into electricity again, which could help in some way to run this computer.
Right. So we looked at it while I was at Intel before. If I remember the number right, you will be able to convert like 17% back to electricity or something like that.
Okay.
So in a way, computing converts the most efficient to least efficient. Then we are converting it back, as you pointed out, Dayalan. You are better off not using all the electricity in the first place. So
Mm.
that 17% you are converting back, why don't you reduce the energy of compute by 20%? Because the thermoelectric circuit is hard, you need to integrate more materials. It is doable, it's doable. But it's more cost, more materials, more manufacturing. So I think it
Okay.
is given you have already wasted it, it is good to recover. I
All right.
agree with that. But my point is, why waste in the first place?
That's fine. Yeah, that's really a fair point. Yeah. Yeah, I think it was an excellent talk, and you really shared a lot of good information related to that. So,
Thank
you
you.
have any final comments before we conclude the session?
No, I would say is thank you very much for, I mean, thanks for doing it. You are doing all this in the current climate, both climate outside and climate politically. So I think I commend the organizers for being this thoughtful in putting together these topics. Please continue to push this because their computing essentially affects people's lives. Even in cities like London, on hot days, they switch off computers in hospitals last 2 summers back. So it's a real problem and it needs to be addressed. So I think kudos to you and to your organizing team for putting this together and getting people together.
All right. Thank you,
And
Professor Shankar.
I'm reachable if you have any questions or any follow-ups. I would be glad to.
Sure, sure, sure. Thank you so much for the interesting talk, and we look forward to more engagements with you in this forum. Thank you.
Thank you.
Thank you. Um, Charlie, Ipshita, over to you. If you have any further comments before concluding today's sessions.
No further comments. I think it was a very interesting talk, and we'll have some more talks tomorrow.
All right. Thank you, everyone, and we'll see you all tomorrow.